How are you doing today, Tony?
I'm doing very well, thank you. Thank you for having us here.
Well, thank you for joining me. So I understand you're working on multi-domain system modeling, simulating systems where multiple physical phenomena interact simultaneously. So from what I understand, MathWorks has done this before with EVs, power grids, utilities, microgrids, renewables. Um, I believe in this discussion, we're focused more on what's known as probabilistic load flow, or PLF. Um, can you cover what PLF actually is and how this technology offers data center gains?
Well, actually, it's not really PLF that we're looking at with AI data centers. Okay,
Oh, okay.
I know
Well,
you asked
that's
that
good to
question.
know.
It's a really good question, and we could probably come
Yeah.
back to it at the end because there is a small place where that could be playing in the future.
Mm,
But for the AI data centers, we're actually doing full electrical simulation. This is
okay.
going from the power grid, through all the equipment right into the rack servers, right? And for us, when we look at this, we call it the electrical power train. Two words on powertrain. Just how does electricity go from the grid and it gets consumed by the data center and then is converted into tokens. That's just the big concern right now is how do you get the maximum amount of compute power tokens out of the watts you're using? And this is where MathWorks, we have lots of experience at helping customers understand what that's going to be, how to model and simulate that. And it's somewhat of a complex ecosystem today, what the AI data center represents. You've got the people who are providing the electricity, the utilities. They're managed by, some kind of system operator who's concerned about these very large loads appearing on their grid. You have the data center operators who are investigating multiple types of configurations.
Yeah.
They have to include cooling in there.
Yeah.
And then you have the people who are making all the electrical equipment and the cooling equipment. So
Mhm.
that's kind of what we look at when we think of AI data centers. And our focus is, in that equation token per watts,
Yeah.
we're focused on the watts part of it. We want to help
Yeah.
customers do that. So I'll stop there. I mean, I know I kind of changed your pivoted a little bit here, but it's
Yeah,
still
certainly. But it's
okay.
okay. No,
It,
it's okay. Yeah.
all right.
It's helpful to know.
Okay.
No, no, no. No, I appreciate it. Maybe we can talk about, there's tools out there like Cadence's Reality DC, digital twin, and that's used to, I think, simulate cooling and airflow, and then NVIDIA's Omniverse, which takes the problem from the compute side. Where does MathWorks kind of sit relative to those tools, and is it a different
That's a good
problem? Yeah.
Good question. All right. A lot of those tools, that software is almost like looking at a 3D aspect, whether
Yeah.
it's CFD,
Mm.
or, the layout and how things are going to be wired together.
Yeah.
Those companies are, looking at, to help customers understand what the physical layout's going to be.
Mhm.
So MathWorks tools actually work at a 1D level, right? Um, a lot of those tools live in what we call the FEA world, partial differential equation.
Mhm.
You get a little geeky here. We lived in the ordinary differential equation world. Everything for us is a lumped parameter. And
Mm,
so, but it's what you need when you're dealing with these highly dynamic systems because
mm,
you have very complex behavior going on. And to model that, you don't want to you want to use an ODE type solver, and that's what MathWorks provides. Our tools
mm,
are help you model the electrical, the thermal part of it. That's at the physical layer of what's going to happen, the behavior, right? But also there are aspects of control in there. We can help customers model that,
mm, mm.
including how to model faults in
Okay.
the electrical system so that you can develop the appropriate compensation to handle the fault. It could be
Mm,
like switching over to a different power system or taking a power converter out of service, something like that. And so that's our whole multi-domain look at this. And when you do that, there are actually different levels of model fidelity that you care about.
Okay.
Right? And this is really important. And where, again, what MathWorks does really well is, let's just take a power converter, right? It's a lot of semiconductors in there, a switching device, right? We're all familiar with these things. So from the AI data center, they want to have models of these power converter devices. Maybe it's some new solid state transformer that one of their suppliers has developed, right? But they don't need to know all the switching electronics. They don't need to see the waveform in terms of the switching. They just need an average waveform. They maybe need something just an average power, right? Because they're just trying to say, how much electricity do we need? How much cooling are we going to need for the amount of electricity? They're doing a rough pass, right? Looking at configurations. The utility, on the other hand, may be saying, well, I'd like to see something in an EMT state. I want to know waveforms. I want to know, is this AI data center going to put harmonics onto my power grid? Is it going to cause instability? Do you have the proper protection there? Right. Now, if I'm the company developing that solid state transformer, I want to see all types of switching behavior, right? I want to know, how efficient this is going to be. I'm doing my control design. I could use ideal switching, just say every pulse is a 1-0, but I need to be able to see that, right? And this is important because one of the things we're seeing when we talk to the hyperscalers and the equipment companies is they can use our product, Simulink, right? That's the main simulation product. As a way to do their analysis or the design, but they want to use it also to transfer IP, right? And so I may, if I'm doing if I'm a component maker or I'm doing maybe a chiller, I would like to be able to provide a model to my customer that protects my IP, gives them the right level of fidelity for the study they're doing. And this way, I'm not having to reinvent IP. My customer trusts that I'm using my design, for them to use. It's almost like an executable data sheet is a way to think about this, right? I can put this model together and hit a play button, and I'm running my simulation. And this is really important because now I can take all kinds of inputs. I can say, well, what if I'm going to use different cooling architectures, right? And maybe some of it depends on environmental conditions, like, time of year, right? If I'm doing air cooling, and so I can start to do large simulations over long periods of time. And that might be more important for the data center to kind of say, okay, let's do a study looking at a year's worth of simulation. I'm going to do hours in terms. That's my time step will be hours, right? Whereas the company developing the equipment, I'm at milliseconds, microseconds that I need to do simulation. Right. But MathWorks software allows companies to do that in that kind of study, and that means we're in a good place to help customers, transfer IP back and forth and ask the right questions.
With that different levels of fidelity, as you were saying.
Exactly.
So you've got the system levels designers working with Simulink to say make these components like solid state transformers and chillers, as you were describing. And then they just have those. Just make sure. Let me know if I'm misunderstanding. So they have those output waveforms where essentially users can just drop those in and have those output waveforms without revealing the IP, and then drop them into their simulation and create that larger data center simulation over with a time step of hours over the span of years. Am I correct in understanding?
They can essentially. Yeah, that's correct. And it's never the same. Each time we talk to a hyperscaler, they have a different slant on what they're thinking about, what they're concerned about. And so, but again, the flexibility is there. We don't pre-build everything. We give you the basics that allow a customer to build up from whatever level they want. Give me a something functional from my my supplier, or here's my here are the IGBTs or the MOSFETs I'm going to use. Here's the processor I plan to use. Let me design around that. And the whole point is, the more I can do in design, I find my mistakes in simulation, right? It's every engineer's dream is to find the mistakes before they start doing hardware testing. Right? Or if you're the data center, when you start, putting equipment together, you want to make sure you're confident that you're going to meet those efficiency targets. Right?
Yeah.
I think when you gave us some, you provided some information ahead of time, and you quoted Jensen Huang.
Yeah, I did. Yeah, the tokens per watt, right?
Right, and it's
metric.
not, that's it. For MathWorks, it's an interesting perspective, and why we feel we do well with these kinds of customers, because he even used the word AI factory, the phrase AI factory. And when you think about a factory, it's almost like foreshadowing that AI is going to become a commodity, right? And so if the market starts to set the price of what you're going to pay for tokens, you want to make sure you only can start to control your costs, right? That's where your profit's going to come from and I think that's what he's looking at, in thinking in some ways that, I need to get as much compute out of that watt as I possibly can, right? Everybody needs to, right? We can't afford to waste those, right?
Yeah.
So it's
actually, speaking along that, where do you see, where in the chain do you typically find the biggest efficiency losses? The data from your perspective, are there areas of improvement that you see that maybe operators aren't necessarily aware of?
Well, in terms of the upfront design, I think a lot of it is in the heating right now. It's just, that's why we like to include the cooling part of this in that powertrain, because what do we say, like 40% of your electricity is going into running the cooling, and so that's where the focus seems to be up front now in the design. I mean, the power converters are very efficient, 98%, 99%. So there's not a lot of losses there. The move from, kind of traditional transformers to these solid state transformers is another big efficiency gain. But at the end of it, any place they can reduce the amount of heat being generated and the amount of cooling they have to put into the system is just savings for them. And they are trying to make these, if you read, they're making these data centers very dense, right? And so that's
cooling
where, kind of the focus is. And that's why, you'll see they do CFD, right? On, computational fluid dynamics type of the data center itself. But we can produce, there's standard calculations for determining, how much heat's being generated in electrical circuits. So we can include that right in when you're doing your electrical study, you can include the thermal in there. Then you can decide, well, okay, this is at, down at, different levels of, you've got the bus bar heating, you've got down to the different zonal heatings down at the rack. So you can determine, how much cooling you need at different levels, right? And, you can begin to, again, plan for those kinds of studies, ahead of time, or plan for that type of heat load. What kind of cooling system do I need here? Can I get away with some type of air cooling here? And again, doing those design trade-offs very early and be able to vary inputs, change, different pieces of equipment in the simulation and decide what's going to be the best for this particular data center at this site.
Yeah. You mentioned earlier that, the different hyperscalers that you speak to often take a different slant to the problem. Do you have maybe an example? You don't have to necessarily name the specific hyperscaler, but just, kind of the different approaches that you've seen.
Well, some really have gotten into modeling the actual power converters they want to see for themselves. What because they are planning, some of the rack designs. Some are much more interested in the cooling. They're doing trade-offs between, do I use a cooling tower, type evaporative?
Yeah.
They want to move away from evaporative type heating, cooling, because it's a big waste of water. Some want to try different chiller configurations, and so that's where they all have different teams, right?
Yeah.
Some are looking at the data center as a unit connected to the grid, and
I
what
see.
that's going to mean, because this is an interesting part of this ecosystem, is that
Yeah.
I read this. I'm not going to say MathWorks, came up with this idea on our own, but someone wrote that, these data centers are essentially large microgrids, right? They have their own energy, production on there. They're connecting, either diesel generators or gas turbines, but they're driving their own generation. They're storing it in large battery energy storage systems. And so they have the ability to produce a lot of power, and they're connected to the grid. Now, any other microgrid, the utilities usually say, give me a simulation, show me what this power, this power plant is going to do when it connects to my grid. But the data centers haven't been doing that yet, and I think there's going to come a point.
Yeah,
Go ahead.
that was actually one of my questions. It kind of led to it, that data center power interconnection timelines, they can be multiple years.
Right.
So how does MathWorks modeling software help with that?
Well, we can. Again, we would produce. You could model out your data center. Whatever EMT effects that the data center can produce, you could model that. Typically, the utilities would want, they have their own particular model format they want. And so what we can do is produce either what's called a functional mock-up unit, FMU. It's a standard.
Okay.
Another thing, our software actually can generate C code. Very efficient C code. Now, typically that's used for controls, but you can generate a model of this and provide it as a DLL, which can be incorporated into other simulation tools. I mean, there's some of the utilities are looking for a true EMT type study. Some just power flow, right? But MathWorks can provide output for those. It's just part of what we do. We recognize we're not the only software on the planet, so we like to work with all the others.
MathWorks is used quite often, in the power electronics world. Plex and Simulink, or I imagine there's that basis there for sure to build off of.
Right. Yeah, we do. That's our big part of our electrical business is the power electronic control design. This is anytime there's any kind of power converter, there's a chance MathWorks software is being used there, not just for the design, but also for, real-time testing, which is, again, generating either the control code or the plant model, as a real-time, and you're testing your real controller board, or in some cases, direct implementation. They're taking embedded code right from our software. It's highly optimized, and they can just target number of microcontrollers or an FPGA, if that's what the kind of speed they need. So yeah, we're pretty. That's why we're pretty involved in this whole ecosystem. And as I said, we are in a nice position that we can help all the participants, move IP between each other, and protect it at the same time. So
Mm.
yeah.
Very, very cool. So do you normally maybe engage at the architecture phase, the design phase, or do you diagnose problems, or is it really just kind of throughout the entire life cycle of the
Well,
data
so
center?
far we've been mostly in the front end of the design, the
Mm.
architecture phase, right?
Yeah.
As these facilities come online, and if they've done the design phase, they should be able to go back. They've created basically a digital twin already, right? Any simulation model is a digital twin,
Yeah.
and they could, say we expect our facility should be running like this, using this much electricity or this much cooling, but it's not,
Yeah.
and then
Mm.
use the, and actually use the simulation model to troubleshoot, to begin to isolate. Okay, let's,
Mm.
what you really want to do is reproduce what you're seeing in the field with a digital twin.
Yeah.
And
Yeah.
again, Simulink would allow them to feed actual data in as inputs, and they could compare outputs.
Mm.
And you don't want it to be a complete,
So they would compare outputs, that they're getting via, say, Simulink, with what they're getting in their in real life,
right. Yeah,
versus
exactly.
their digital twin.
Right.
So it's just kind of having redundancy in terms of and comparing data between different platforms. Am I understanding this correctly?
Yeah. I mean,
Yeah.
there's going to be some operating system, some DCS that's going to
Mm.
operate the power system and the cooling
Mm.
system, and there'll be a historian collecting data.
Mm.
But you could take those inputs from the historian, run it through the model,
Mm.
and compare the outputs in the historian and to what you're getting in from the simulation. And at that point, you could start. And we've had customers do this. They'll make
Mm.
an adjustment and say, "Can I reproduce what I'm actually seeing facility do?" And that helps them
Mm.
isolate. Okay, here's the problem, right? Okay,
Mm.
it's really these settings here on our in the cooling system that's causing the problem, because these
Yeah.
facilities are going to be huge, and
Mm. Yeah.
tracing the problems it can be difficult, right? And we've had customers that do this in all types of process operations. They'll see some kind of cyclic behavior, and they do some kind of FFT, and next thing you know, they've said, oh yeah, it's the same frequency that
Mm.
this piece of equipment's operating on. Let's go check there. And
Mm.
so I think in the future that will help. Um,
Yeah.
we offer software in our MATLAB side that will help customers do
Mm.
anomaly detection,
Okay.
predictive maintenance. That's something they would have to incorporate into their own system. But if they pull
Mm.
the data, they can say, okay, this is look, this is happening,
Yeah.
and actually begin to troubleshoot and determine where it's occurring in the system.
Maybe you can run through an example. How about this, of what you were just explaining? Really, just the gaps that you're seeing, customers are seeing in their data center, and how they use MathWorks multi-domain simulation tools to
Well,
assist with that.
I can give you an example of
Yeah.
an equipment manufacturer who uses our software
Mhm.
to develop basically their compressor units, right?
Mm.
But they have them all over the world, and so they look at that fleet of compressors, that they want to help their customers maintain operation, right?
Yeah.
And so they're always monitoring those
Mm.
compressors. They take the data in, and they're
Mm.
using, because they know the models, they know
Mm.
how these things should be operating. They can start to use that to predict when a unit is starting to have some type of failure, and they've
Mhm.
learned it very extremely well, the different types of failures and what to look for in the models. And that way they can go back to their customers and say, hey, next chance this unit's available, it needs this kind of repairs,
Mm.
versus letting it fail in the field.
Mm.
And then you've shut down some operating facility that's depending
Yeah.
on this. Yeah, this will happen. I believe in these AI factories. They have to, these data centers.
Mhm.
They'll want to know when a piece of equipment is nearing failure. how they outsource, whether they'll go to the different OEMs that are providing the equipment, or whether they'll try to do it, at their own, at a, kind of the data center level. But this is exactly what you would expect them to be able to do. But they do need a model, right? Probably the trickiest part in our business is when a customer says, "Oh, we want to be able to do this," but they have to learn how to model their equipment. And usually, it's not a lot of time. They're very comfortable when they they have CAD models, right? That's what a lot of people think models. FEA, CAD. Well, but you need dynamic behavioral models to be able to do this, right? And model to the level of where the failures might occur. If you masked over something and kind of made it not provide enough fidelity, you really can't predict where the failure would occur.
Gotcha. Yeah.
But this will be an important thing. Again, I go back to it is a factory. It's got capital equipment in there, and they need to monitor it. And anytime something goes down or begins to fail, they have to reduce how much computation it's able to do, and that's losses to the factory.
Is there anything that I might have missed during the interview? Any questions I didn't ask? Anything you wanted to clarify or kind of talk about?
Well, I just on your PLF question. Actually, it's maybe for another time, but the reason that we were involved in that, right?
With Eversource, right?
With Eversource. Now, Eversource is at the distribution level. The wooden telephone poles, right? Not the big steel ones. Okay.
Yeah.
And but what they're seeing is that with the advancements in electric vehicles, heat pumps, solar, there's so much power electronics going into the network, basically inverter-based resources. And they can't model all that. It's just, you can't come up with an EMT model, right? They have a power flow model, right? And it's in a third-party software that they use. And what they did was they used MATLAB to build, Monte Carlo analysis around that power flow. It's too massive of a, if you could model it, the computation would, you'd be waiting days, I mean, it's a very specialized area.
Yeah.
But they use this like basically a power flow, software, and they said, well, we want to automate this, and so we helped them build a lot of automation to do this probabilistic load flow kind of analysis, so they could say, okay, and what it actually allows them to do is identify where the grid has the most potential for failure or needs to have new equipment in there, or where there's too much traffic, power flow through there. They just don't have the capacity. And why this is interesting was we saw a question that came in that said, well, there are some companies that are starting to look at, well, what if you could put like mini AI data centers that take near homes, right? So to take advantage of that, a house doesn't use all the electricity that could possibly come to it. And when you asked the PLF question, I was thinking, well, that's really how you might analyze that, right? If you start distributing AI throughout, you can have all these power converters, right, throughout the network, because you've got to go AC to DC, right? And again, it's just like what, it's another problem for someone like Eversource, and like, okay, there's, another 10,000 inverter-based resources on my network, and so I need to figure this out. So it's not out of the realm that people are going to have to, if depending on what happens with AI data centers as it become distributed. We don't know yet. It's a potential. So it's a good question. Interesting question. Made us think about it.
Food for thought. Well, honestly, I didn't realize I didn't realize it was a food for thought question. I just asked because I just sort of assumed it would be PLF in my head, and but it is an interesting statement that you just made.
Well, I mean, if you were going to look for, I mean, you can go back. You know, we have like a good reference would be what we do with Siemens Power.
Okay.
You know, Siemens is designing, you know, FACTS and HVD systems to connect
Hmm.
offshore wind, onshore wind,
Hmm.
solar, you know, into the grid. And they use our software, you know, to
Hmm.
develop all the controls for that equipment. They're modeling the whole
Okay.
system, right?
Yeah.
Again, it's not, you know, in terms of the technology, it's not that much different than an AI data center, right? You know,
Hmm.
I mean, they talk high voltage DC, and what really AI data centers, when they talk about some of these newer solid state transformers, low voltage DC, you know, they want to go from
Yeah. 800 to 800.
34.5K AC down to
Hmm.
800 volts DC. Well, that's
Hmm.
just, you know, that's kind of what a high voltage DC system does. It takes
Mm.
AC, you know, high voltage DC. In this case, it's low voltage DC.
Yeah. Well, thank you so much for your time, Tony. I really appreciate it. This has been a
Well,
really
thank
helpful
you.
conversation. And
Yeah, it
I
was
really
fun.
thank you for your being, candid and, answering my questions. And,
No, no,
I
it's
really
great. No,
appreciate it.
we really look forward to this. Thank you very much.